Oh wow, this is a nice and bright, beautiful sunny day. It's hard to believe it went from -20 last night to +6 right now, sitting here in the sun. I only have a few more days to be here, so I better take it in while I'm here. All right, let's get some NABU stuff done. What's going on, my NABUers? Today is kind of fun because last night I realized a few things about how the data transfer on the UART, the HECA, of the NABU works to the network adapter. I also got myself this little tiny TV because I was having issues with my video capture card, so this is actually kind of fun. I picked it up on Marketplace. And look, the lady even had the original manuals and the warranty slip, which she didn't fill out. So I'm going to fill that out from 1995 or whatever this is and send it in. I think that'll be hilarious. So let me show you something first. I'll just start up CPM here because what I've done is originally I had the receive timer, the receive loop, actually count on a timer for timeouts. And that would happen for every byte. And then what would happen is if it timed out, it would present a message to the user with an error code. And that error code would tell you where it actually crashed. Now, I found that was actually giving me issues. So what was happening is that this little computer is only running at 3 megahertz, okay? And the communication speed is 111 kilobits per second. So there's really less than 100 or so cycles available per byte coming through. So when you think about how many cycles a single command would take, like if you convert this, for example, into assembler, this essentially is loading A with the address of the port, right? So port A, and then you have to out your whatever the HECA port is, my interrupt mask, okay? So this is kind of like, there's two calls per one of these, right, in assembly. And this takes, I think it's 8 or 12 of cycles, right? This takes, I think, 16 cycles. So just doing one, like just latching the port takes already 30, 40 cycles. All right, so as soon as you start getting into doing while loops, especially 16-bit or 32-bit counters, because you need to do a count to like 1,000,000 for a 20-second timeout. So when you start doing that, you end up using so many CPU cycles that we should be looking at read byte here. That's the one that matters. There it is. So I used to have a timer in here, right? So as I would count down and count up, it would catch the data, and then as it was trying to do the counter and process the data, the next bit of data that came through, it was missing it. Right, so that was actually causing an issue, and it wouldn't happen all the time, just on occasion, specifically for Linux users at the 115.200 baud rate. Now, John from John's Basement had asked a question about what this code is doing. So on the transmit side, I'm not doing a timer, and this is not what this is. This is actually latching to port B, because port B is a reading port, okay? See, I set the interrupt mask to just the TX. So it's checking to see if the transmit bit is set. When it is set, that means there is data being transmitted. Once this goes away, and this is unset, this bit is unset, then there is no data being transmitted. That means that the buffer has been cleared, the TX buffer. So this waits until the previous TX has been completed, okay? And then we do our write, and then this turns the interrupt back into an RX so that the RX would work. All right, so it's better to turn the RX on after transmit than turn it on in here, because otherwise you can call to read, but something might have happened since then. So if we take a quick look at our NABU technical manual from MGP, what we're going to see here is some information about the port A and port B right here, okay? So this is what I'm checking. So port A is write only. This is where you can specify what interrupts you want to listen to. So I could say I want to listen to the keyboard, and that's it. And that's what I'm doing in CPM. I'm just using the keyboard interrupt, for example. And then what'll happen is it'll execute, I'm using IM2 mode, so it'll execute a piece of code. We went over that in another video. I recommend checking that other video. And then, but in order to check what I just had showed you about the bit, if the bit's been completed or not, is through here. So I can actually check to see if, and it does, it's interesting that it sets it through the third bit here, which is A2 priority. Okay, so this is the bit that is used for TX. Okay, so that covers what I had been going through to solve a pretty big deal with data transmission for the remote file system of CP/M. Reliability is like 100% now. I had not had a single crash. I've been pretty happy with that. So that's great. Now the next thing I want to show you here is VT100 emulation. Okay, so John had asked in a post, why do we need VT100 emulation in the BIOS? And even Leo on the phone yesterday or 2 days ago, he mentioned the same thing. What would you need VT emulation on the BIOS of CP/M for? Well, that's an interesting thing because CP/M, just like the original MS-DOS, has no way of being able to specify where the cursor is going to move on the screen or any text formatting at all. Okay? And that is because later on in years of computing, there was a program that came out, you might remember, called ANSI.sys. And what that would do is you'd load that into DOS and it would give you the ability to have colors and move the mouse cursor around and everything. Before this, the only way to move the mouse cursor around or format the screen was to talk directly to the graphics card, or in this case with the NABU, the VDP. And because CP/M is made to be an agnostic operating system, there are no function calls in the BIOS to move a cursor around. And CP/M itself has no way of knowing what kind of video card you're running, because whenever you think about CP/M, it's always on a WISE terminal or a DEC terminal or some sort of terminal, some dumb terminal, right? It was always on some sort of serial connection. And so when you played old games or used WordStar or something, it was because this was actually on a computer that did emulation. And that's not where we're at with the NABU, because the NABU didn't have it. So let's first demonstrate what a program would look like without emulation. So you might have seen this in some of the example programs I've included. So what I'll do here is I'm going to go through my VT emulation code here, and I'm going to comment out the part that checks to see if it needs to emulate. And now we're going to go into our BIOS code here, and we're going to build the BIOS. And then I have a VT test program here, which I'll build. And now I can get back over to the NABU, and we're going to restart it. This is going to boot the BIOS where we just disabled my VT emulation that's built into the BIOS. Now we're going to run our VT test program. And you see what's happening. Every time I push space, you see all these characters on the screen? You probably recognize that from some of the programs that you've ran. There's nothing happening, just all this stuff. Now these are VT100 and ANSI characters, or encoding. So this actually is telling the encoder, or the decoder, sorry, where to place the cursor. In this case, it's saying 12th row, 5th column. That's how it's going. It's opposite of XY, it's YZ, and with an H on the end. And I will show you what this exact same program looks like with my VT emulation enabled. So now we're going to rebuild just the BIOS we only need to rebuild. And now we're going to reboot the NABU again. And let's jump back into our VT test program. And look at this. I'm at line 2 by 1. And then we got a nice little space prompting us to do space down here. And every time I hit it, something's happening on the screen. There's things going to different places. Okay, let's complain a little bit about VT emulation and how it is the absolute worst protocol I've ever had to deal with. Now, that might not be actually completely true because it's the most recent in my mind. So let's take a quick look at a manual page of what the VT and ANSI communication escape protocol looks like, the escape sequences. Now, I don't know who was smoking crack when they came up with this, but it is completely backwards from any protocol that I've ever used or would ever have thought of. Well, you need to parse this in reverse. You would think that the command would come before the parameters, and that way you would know what the command is, so then you know what parameters you're supposed to expect. But in this case, you have to keep track through a state machine of every single character you've received until when you start getting an escape, so you start receiving and keeping everything into a buffer. So you're using extra memory space because of that, and then you have to hold on to it until you get a last character. Now the thing is, what if there's a character that you didn't realize you're not handling, okay? In which case, you just have to wait for the buffer to fill up, and then what do you do with that buffer? I guess you just dump it to the screen. That's what I'm doing. So if there's a letter that, like a function that I'm missing because I went through these documents, maybe I'm missing one, I have no idea. So you can easily lose track of things because they put the silly function at the end of the protocol block. That is ridiculous. So let me show you how I solve that problem. What I have in my code is a VT history, and what I do is, as every data byte that comes through, I add it to a circular buffer. Now actually this is quicker than using a for loop. That's why it's like this, if you're wondering, okay? This is faster than using a for loop for such a small number of items. If it was a larger count of items, it would make more sense putting a for loop. So copy and paste, copy and paste. These are some of the things you learn. I come from assembler, so when I start realizing how fast and slow certain functions can be, sometimes it's quicker to do things in inline, okay? So what I ended up having to do is every time a character comes through, I first process it to see if it's a new line or anything, right? Because that's simple stuff. Or a backspace, because the backspace isn't processed by the emulation. And also clearing the screen for basic. Basic doesn't use the VT100 or ANSI emulation. It always uses 12, as you remember. So that's in there. And of course our little ding-a-ding bell. And then I return from any of these because these are all things that are not ANSI or VT100 related. They're just part of the terminal. Now I say, so are we like in a position where we're not parsing a line because we've never received an escape before? And the character that just came in, is it also not an escape? If that's the case, we just write the character to the screen because we're not escaped and this character coming in is not escaped. Okay? Now I say, if this is an escape, because this is the first time we've received an escape, it must be the first occurrence, because the C is the most recent character that's just come in. So therefore, we clear the buffer with nulls, we reset our parameters, and we add the character to our revolving door buffer, so our circular buffer. And then this is interesting. If we are in an escape mode, and our escape size is the same size as our history size, like our buffer, we're at the end of that buffer, well, that means we must have received some sort of character during escape mode that we are not handling. So therefore, we just write out what we have into the buffer, and that's it. And then we saw our circular buffer. And then finally, I increase our position of the buffer for the next character that comes through. Okay, because this is telling us where our escape position is, meaning that if an escape character was C, the next time, this time it'll be on 0, but the next time this runs, it's going to get moved to position 1. So I'm always keeping track of where that escape position is, because that's where I start counting back from to realize what's inside of our escape mode. And then if it has one of these, a square bracket, that means that what we received is a parameter function. Otherwise, it is not a parameter function. So what I'm doing is, when you parse it through with there's no bracket, all I do is I check to see the very first byte, which is my most recent byte, and I say this, because if it's the end of a command packet, then one of these should be that letter, one of these letters, right? And in this case, let's scroll up. This one is the one that doesn't have the square brackets, so these ones are not very interesting. But we'll get up here. Let me go to the top of this one. This one is the one that has a square bracket. So it looks like long code, but it's actually pretty quick and pretty efficient, because all I have to do here is I switch on the most recent byte, and I just say, is it a C? If that's a C, then we know that it is a request to identify the terminal type. And I used to send this information. It doesn't matter if I send it or not. It doesn't seem like any programs care about that. So I can remove a little bit. I could save some space in the BIOS by not needing that. And then we have our, is it a N? This is requesting the cursor position. I could not find any code that actually did this as well, requested the cursor position. Everything I tested seemed to work fine. I'll add it back in if I get into tests where it doesn't. And then move the cursor up, for example. So this is saying populate the args. Well, this is interesting because remember, I have to parse this line after I've received it, and then I don't know what's in it until I get this last character. And then I have to parse this from the forwards direction, so reverse from what I've received it, or I guess the same direction I've received it, but the reverse from how I've stored it. And then I have to read through it, and I have to parse ASCII characters and convert them into real numbers, so into values. So what I do in here, populate args, is shrink back a bit so you can see the whole thing on the screen. There we go. Well, I know there's going to be at least 2 parameters in here. So I have an array with 2 parameters. I loop from the escape position backwards towards the beginning. If it is a digit, okay, now I'm not using isDigit because isDigit will also check for A, B, C, it'll check for hex values. We're not going to be checking for hex values because there are no hex values. So I have to use, and also useDigit or isDigit in C is STLib or something, and I'm not including those libraries in any of this because we are trying to treat BIOS as small as we can. So I check to say, is it a character or a number, sorry, and then if it's the second position, then I multiply that by 10 because it's going to be like a 10, a 20, a 30, etc. Otherwise, I just take the value, I subtract it by its ASCII value, and that gives me its real number. Then I increase the position, and then the loop goes again. But this time, if the loop doesn't get a digit, instead it gets a semicolon, then I increment our number. So now we're going to be talking to arg number index 1 versus 2, or 0. And I also reset our position, and then we do it again. Now, if I get, for some reason, multiple semicolons in here, well, I don't process anything with multiple semicolons because that's stuff like colors and things, and we don't have colors on the NABU. So therefore, I just exit. I just get out of here. Okay, and then we get back into our code. Now, I know after running this that args0 is going to either be a value of 0, meaning that there was no argument passed. It was just an escape A. Because remember, a lot of these codes are optional arguments. For example, look at this one. Escape A with a number sign. Move the cursor up, number of lines. It doesn't have to put a number in there. It could just say escape A with no number. And in that case, I need to know that. So I check here. If I parsed it and that came back with a 0, then it must mean there's a 1. That's the default value. And then we move up. Okay? So I have to do this through all of the different commands for ASCII and VT100. So things like moving the cursor up a number of times, move the cursor to a specific column. Some of these have multiple commands. Oh, these are unsupported. So I just say I have to capture them, because if I don't capture them, then I hold on to that data in the buffer and I don't write it out to the screen until that buffer gets full. Like I said, in which case I could be missing bytes. So I have to capture everything, even if it's not supported. And save the cursor position. And of course, there's a couple different ones. Like if you look at this one, this K has either no parameter, we'll do this, or with a parameter, we'll do this, and with this parameter. So it's like afterthought for them on what they thought these different things should do. There's no rhyme or reason to it, it seems. And also, if we take a look at H, this one, H and F do the exact same thing. Exact same parameters, everything's the same. So yeah, that's interesting. So I gotta say, this is my little rant about how terrible VT emulation is. What an afterthought, I swear. So that being said, we covered a couple things in this video. One, the CPM, Cloud CPM is friggin' awesome right now. It's running really great. There is a beta version of emulation inside of the BIOS, so I definitely recommend you give it a shot. I will be adding a few more things to it. The next thing I'm going to be adding, which is not in here yet, is my scrolling. I did have scrolling in my Telnet and emulation, which is using VT emulation too. I just didn't have time last night because I had other things to do, but that's not a big deal. So what I mean by scrolling is that there are parameters you can specify of where the scrolling window starts and ends. And it's in here someplace. This, actually, I don't think this document even explains it. I think that's in another one. Let's see here. Erase from cursor, blah, blah, blah. Yeah, this one isn't the one that tells you about scrolling. So, like I mentioned earlier, every document is just like, hey, yeah, I'll just talk about what I think is interesting. The internet, eh? Okay, so we got cursor up and down. Oh, here we go. Set scroll regions. So this is important specifically for editors. And that's easy for me to do because I already have a scroll function that is built into the BIOS under... I took it from NABU lib. And, oh, actually, no, I moved it into VT100 because all my video is in here now. So let's take a look. We have write character, set cursor. This is mostly from NABU lib if you guys are interested to see my scrolling code and how everything works. Where is my scrolling code? Right. Text up. Here we go. So I had mentioned this numerous times before, is I use a double buffer for text because the VDP in the NABU has its own RAM, which means the only way to talk to the RAM on the video chip is through the video chip. So if you want to write to the RAM, read from the RAM, write to the RAM every byte to move everything up one, you have to do that talking to the video chip. And that means you have to latch the chip to specify the address, read the address, latch the chip to specify the new address, write the address. This goes on and on and on, back and forth, back and forth. So it takes up a ton of CPU. My first versions of scrolling was very, very slow. And I was at an awe because I didn't really consider that as being a challenge, figuring that the VDP would be able to have some sort of memory copy buffer routine or something. It does not. So there's no like DMA, right? So what I do is I keep a text buffer. So every time I write to the screen, I need to use a text buffer. But reading from the screen, I can also use that text buffer. So this makes it super fast because this is in RAM. This is on video RAM. This is on system RAM. So what I have to do to scroll is take characters from system RAM and move them directly into video RAM. And why this is super fast is because with the VDP, and this is something I was mentioning to John on John's basement, is that you only need to specify the latch address, the address you want to write to, once, because every consecutive byte you write to the VDP, it'll increment its memory address. So I don't have to latch it through in this loop over and over again. I only have to latch it once, and every time I write to it, it will actually increment. That's what makes my scrolling routines so frigging quick. Anyway, we got off topic here, but the scroll takes a top row and a bottom row. So all I have to do is keep these two values, which I already have in code, like the top row and bottom row. Right now it's using the full screen. All I have to do is assign those values to what I get out of here. And then only that one region will scroll, and nothing else will, right? Top row and bottom row. So that's my next thing I have to do. I know it's not super complicated. I'll get to that today. Got a few other things to do right now, but you might see it tonight. So if we take a look through, this is all the stuff I have to deal with. Look at all these commands. Look at them all. Look, turning on and off LEDs. Like, geez, Murphy. Anyway, so yeah, that's us for some CPM, some emulation. I gotta actually go and play a little bit of Hitchhiker's Guide now that I just brought that up. I'm gonna do that for a bit, and I'll see you guys in the next video. Bye-bye.